Explorers, welcome back to Virtual MOSI. My name's Catherine, and today we are going to be kicking off our chemistry week by talking all about atoms and the states of matter. Now remember, never trust an atom. They make up everything. And we'd also love to hear a little bit more about you. If you want to comment down in the comments where you're from, we're very curious to hear where our viewers are located. So let's get started. First of all, we need to know, what is matter? Well, matter is anything that has mass and takes up volume. In other words, it has stuff and it takes up space. Puppies have mass or matter, chairs have matter, flowers have matter, water, matter, balloons, matter, this is matter, that's matter, but most of all, you matter. Okay. So matter, if we break it down to its smallest component, its littlest building block, that's what we call an atom. And an atom has three important parts. It has protons, neutrons, and electrons. Now the protons and the neutrons are located in the very center, or what we call the nucleus. Each of these particles is a little different from each other. Protons have a positive charge. Electrons have a negative charge, and neutrons have a neutral charge, or no charge at all. So let's get started with our activity today, and we're going to make some model atoms. You can try this on your own at home using things you find around the house. I've come up with two different options for you, but anything you have will work. For example, you can use PlayDoh to make your model atoms. And to keep things a little neater, I've put the PlayDoh onto some paper plates. But you can also choose to make model atoms with marshmallows. Those work very well. And if you want to do that one, another good thing to have is toothpicks. And I have toothpicks of various sizes, but whatever you have will work. So let's make our first model atom. I've made one here, and it is a helium atom. Helium is the second element on the periodic table. We'll talk about that in a second. But helium has 2 protons, 2 neutrons, and 2 little electrons. Remember, the protons and the neutrons are in the nucleus, or the center, and the electrons are circling outside on these rings that we call valence shells. So, let's see here. Every atom on the periodic table has this little descriptor just like this, and it tells you a lot of very important things about the element. For example, what is its name? What is its symbol or abbreviation? What is its atomic number? Now the atomic number is going to match how many protons that atom has. And it's also going to include the atomic mass, kind of how heavy that element is, and it's based on how many protons and neutrons it has. So 11 times 2 plus however much mass its electrons have. Remember, protons are what defines what element we're dealing with. So for example, let me go back here. We have our periodic table. Hydrogen is atomic element number 1. Do you remember what that means? How many protons does it have? That's right, 1. Helium is going to have 2 protons. Something like carbon, for example, is going to have 6. Oxygen will have 8 protons, and so on. Let's look again at my models here. I've already put out the protons for you to see. So, for example, with carbon here, we have 6 protons, and I've also included 6 neutrons and 6 electrons. Oxygen, 8 protons. Sodium, 11 protons, and chlorine, 17 protons. It is a very big element. I'm just going to throw in the neutrons here. That'll keep our protons from having too much opposing positive force against each other, and it'll just help keep our atom nice and tight together. Remember, protons are positive, electrons are negative, and neutrons, of course, are neutral. We'll just combine those there. And if you are making a model of an atom out of marshmallows, you can do that too. It's a little harder to see the difference between the protons and the neutrons because they are the same color, but they're together in the nucleus, and the electrons are circling around the outside. Remember, the protons and the neutrons are so much more massive than those tiny little electrons. I've made helium, and I've also made carbon for you right here. And we'll come back to that in just a second. I wanted to direct you to a fun resource in the meantime that you can try at home. It's called chemspeller.com. If you'll notice, the periodic table all has these fun abbreviations, and I really enjoyed as a kid using it to write secret messages. So if you go to that website, it'll help you figure out how to make those messages a little more easily, or all you need is a periodic table, and you can kind of search along and come up with your own words and write your own secret messages. It's really fun if you want to start out by trying to write your name with the elements. Okay, so let's go again and build a carbon atom, which I've already done here. Again, let me get rid of this and we'll start from scratch. Carbon has atomic element number 6. So how many protons does it need to have? That's right, it needs to have 6 protons. 1, 2, 3, 4, 5, and 6. And in an ideal world, it also has 6 neutrons. And to keep it properly balanced, keeping that charge negative, it's going to have 6 electrons. Now you'll notice that carbon has 2 valence shells. Every shell has a certain number of electrons that it can hold, and in carbon's case, well, in all the cases of that first valence shell, it can only hold 2 electrons. So once there's 2, that whole level is full, and you need to move on to the next shell. So I have 4 left, and that second shell can hold quite a few. It can actually hold up to 8. But all I have left is 4, so that's going there. All right. Now, those are the different atoms and the different types of elements that you can have. And when you combine atoms and elements together, you make molecules. So atoms are smaller than molecules, and they can bond in 2 different ways. They can either have a covalent bond, remember valence electron shells, where they steal electrons to fill up those shell levels, or you can have what's called an ionic bond, and in those cases we share electrons in order to keep the charge neutral. Now let's see here. I wanted to give you a quick example. Water is an excellent example of a covalent bond. So we have 2 hydrogen atoms, two hydrogen atoms, 1 oxygen atom, together make 1 water molecule, H2O. And obviously it's O1, because we only have 1 oxygen. Now, something else like NaCl, for example, are you familiar with that particular molecule? I'll bet you are. NaCl is just the chemical name for regular old table salt. Now, NaCl, salt, has what we call an ionic bond. So it's actually sharing electrons instead of stealing them from one another. Okay. Now let's talk about one other thing to do with our atoms, is states of matter. So first of all, you've all seen the different states of matter. The main 3, we have solids, liquids, and gases. So I've used water as an example of all 3 of those here. So I have solid water, or ice, solid H2O here. And in this case, for solids, it has what you see a definite shape and a definite volume. It's not going to get any bigger or smaller unless it melts into another form. And so you can see those molecules are very tight and compacted together. They don't have a lot of energy to move around. Now liquids, on the other hand, have a bit more heat energy, so they can move around somewhat freely, and they have a little more space between each other. So again, definite volume, but not a definite shape. It has enough wiggle room that liquids can take on the shape of their container. But if you'll notice, I still have exactly the same amount I have about 175 milliliters there, and 175 milliliters there. No matter what container it's in, it has the same volume. Gas, on the other hand, and in this case, I'm trying to show you that I have a little bit of steam, water vapor. You can see it kind of condensing around the outside of that glass. It does not have a definite shape or a definite volume. And those molecules have so much heat energy that they can move all around, and I can compress it. It can take the shape of the room. It can take the volume of whatever container I put it in. Okay. Now I wanted to show you one more cool thing about why I chose to use Play-Doh for this activity as opposed to marshmallows or something. This here is a black light. And what we're going to do is we're going to cut the lights for a second, and we're going to take a look at our different molecules. Ready? It just makes them look so much cooler when they're made out of Play-Doh. So you see here we have sodium and chlorine, which together, sharing their electrons, are going to make salt. And then we have oxygen and two hydrogens, H2O, H2O1, and that's going to make water. And of course, if you combine salt and water together, you get salt water, which is an interesting mixture, and we'll talk more about that tomorrow. Remember, atoms are made of protons, neutrons, and electrons, but I want to go into a little bit more advanced topics of this. Yes, do we have a question?
We do. Can you talk a little bit more about covalent bonds and whether they share electrons?
Yes. Covalent bonds actually steal electrons as opposed to ionic bonds sharing electrons. So you'll notice here, when we have the covalent bond and we have the hydrogen, which has one electron here, that whole outer shell I mentioned, that first valence shell, wishes that it had two electrons. So it's kind of borrowing one, if you will, from the oxygen, which has 1, 2, 3, 4, 5, 6. Oh, it normally has 6 on the outside here, but it's borrowing one from hydrogen, and it's borrowing one from this other hydrogen to fill it up and make 8, because ideally the valence shell has 8 electrons in it. I hope that helps a little bit. Okay. Now we're going to talk about a little more advanced stuff. If you want to at home, you can practice making different basic atoms like we've done, or you can try making some of these special atoms at home as well. You might have mentioned that I said earlier, in an ideal world, our atom is going to have the same amount of neutrons, the same amount of protons, and the same amount of electrons. Well, the world is a messy place, and sometimes that's not the case. We have two special types of atoms called isotopes and ions. An isotope is a particular version of an element defined by the number of neutrons. So, for example, I have used the element boron here, atomic element number 5. So it has to have 5 protons. If it doesn't have 5 protons, it is a different element. So here's the ideal situation. 5 protons, 5 neutrons, 5 electrons. But if it was an isotope, perhaps it doesn't have the normal number of neutrons. You might have 1 extra neutron or 1 missing neutron. And isotopes are often radioactive elements that are not as stable, and they're more prone to breaking down. Ions are actually quite common. In this case, an ion is the form of an element that either has too many or too few electrons. So remember, electrons have a negative charge. So here I have 1, 2, 3, 4, 5, 6 electrons. So we have an extra electron. So if we have an extra negative particle, this whole atom right here is going to have a negative charge. And in this case, my ion is missing an electron. I have only 1, 2, 3, 4. So in that case, we're missing an electron, and we have 5 protons, 4 electrons. So we have a positively charged ion. You can test that out over here if you want to make your own. let's look back at carbon. Now, what would we do if we wanted to make an isotope of carbon? Well, we either need to have an extra or a missing neutron. So this might be a carbon isotope 5. It's missing one of those neutrons. Okay. Or, alternatively, you could have an extra one, and that would be an isotope as well. Now let's talk about ions with this one. If you wanted to make a carbon ion, it would either need a positive charge or a negative charge. What would we need to do if we wanted to have a positively charged carbon ion? Well, we'd need to get rid of one of the electrons, right? So now we have 1, 2, 3, 4, 5 negative particles, and we have 1, 2, 3, 4, 5, 6 positive particles. So this would have a charge of positive 1. If we had an extra electron, maybe carbon for some reason stole it from another atom, what charge would it have now? Well, we have 1, 2, 3, 4, 5, 6, 7 negatively charged particles, and 1, 2, 3, 4, 5, 6 positively charged particles. So in this case, we would have a net charge of negative 1. This is very important when it comes to electricity, something that we're going to talk more about with Thunderbug tomorrow. Okay, one interesting ion that you probably experience a lot in your life is the hydrogen atom. Believe it or not, hydrogen, the first element on the periodic table, is most commonly found in an ion form. You might have noticed when I made it on the table here, I didn't have a single neutron at all. Hydrogen is often found as an ion. It's actually a little more stable in that form because it has one positive particle and one negative particle, so it doesn't need that neutral particle as a buffer as much. Okay, so again, go ahead and try at home. If you want more of a challenge than just building different elements, you can also try building different versions of the isotopes and the ions of that element. Okay, do we have any questions before we finish for the day? None? All right, don't forget, explorers, we'd love to hear where all of our audience is from, so go ahead and comment what state you're from, what country you're from down in the comments below. And if you have any extra questions after this, go ahead and share them and we'll answer them a little later. Thank you again so much for watching, and tune in for more chemistry later this week.